Got the first step. Not gonna wait for anyone else. Not sure who else is coming, so we'll just go. So today we're now focused on we're starting what's called subspace topologies, the first section of this chapter. But big picture, what this chapter is about is constructing new topologies from existing topologies. We don't want to have to start from scratch every time we want to construct a new topology on something. Imagine, for example, I gave you this blob of an object right here. Ignore the blue patches on it, but this is supposed to be some blob surface with some holes in it. And your job is to construct a meaningful topology on that. Now, at first glance, that might not seem like a very intuitive thing to do. Your first thought might be, there's no pretty way to do that. Well, today we're going to start by talking about subspace topologies. And what a subspace topology is going to do is, we know very easily how to talk about the topology on R3, the space we occupy right now. What is our topology on R3? What's our basis for R3? How do we get an open set in R3? Unions of open balls, but three-dimensional open balls, right? So you think about basically a solid ball, but peel off its surface. So it doesn't include that boundary. And any union of open balls that you can create in three-dimensional space would be an open set in R3. And we've already done a lot of work with the standard topology on R3 and on R2 and R1. Done a lot of examples with that. And so with the subspace topology, what we're essentially going to be able to do is piggyback on that topology we already know for R3 to create very natural topologies for shapes like this, for shapes that could somehow be embedded in R3. And it scales up pretty easily. If there's some shape, sure, we can't picture it, but if there's some set that I know how to talk about embedded in like R7, some 7-dimensional surface that I know how to embed in R7, then we can easily talk about topology on it by inheriting from the standard topology on R7. So the first types of topologies we're going to create are called subspace topologies. Those are topologies that are really easy to make if we know how to somehow embed them in a bigger space that we know how to talk about. Typically, we're going to embed them in R2 or R3. So with this shape right here, we embed it in R3, but when you're talking about just let's create a topology on a circle, we can embed it in R2 and get the topology for that. That's what the first one's going to be. Our next section is going to be on product topologies. This is where you're going to have a topology on one set, a topology on another set, and somehow cross-product them together to create a new set, and it automatically inherits a natural topology. One of the ways that we could think about R2 is a cross-product of the two topologies on R1, for example. And then the third section, which will be on quotient topologies. So we have subspace topologies, product topologies, and quotient topologies. Now you might think a quotient topology, that's somehow dividing one topology by another topology. No, it's better to think about them as somehow gluing objects together. So it's kind of like adding two topologies together, even though it's called a quotient topology. You'll understand why it's called a quotient topology, and you'll also understand why we think about it as somehow adding, hooking two topologies together. So topologies that we already know and love, hook them together in some simple way, gives us a new topology that it's easy to talk about. So that's what this chapter is going to be about. Taking topologies we already know and love and using them to talk about other topologies that at first glance it might not be so obvious how we talk about them. So first section, subspace topologies. Here's our definition. Let X together with tau be a topological space, and let Y be some subset of X. So let's get our picture here. Here's X, that's our universe. X has some topology on it. We don't know what the topology is, but maybe, oops, we're outside of X. Maybe this corner here is an open set in X, maybe this is an open set in X, maybe this is an open set in X, who knows? So we've got X together with some topology, some set of open sets. Now we have inside of X some subset right here, Y. Let me make Y a little bit bigger. Let's make Y right here. So here is Y, some subset of X. The subspace topology on Y is going to be, it's a topology it's going to inherit from X. And what its open sets are going to be, let me get another color marker here. What its open sets are going to be are the open sets in X intersected with Y. So notice that this circle here was an open set in X. So an open set in Y is going to be this. just where it intersected y. This was open in x, so this piece right here is going to be open in y. This was open in x, so this piece right here is going to be open in y. This is open in x, so the whole thing is also going to be open in y since the whole thing was inside of y. That's how it's going to be defined. And so this is going to give us a topology now on just y. If we kind of ignore everything outside of y and just look at those sets that intersect y and how they intersect y, we're still going to have a topology. It's called the subspace topology. So first off, we're going to call it the subspace topology, and then I have to prove that it is in fact a topology. But that's pictorially what it's going to be. So with this picture in mind, let's read the definition. So let x tau be a topological space, and let y be some subset of x. We define tau sub y, this is a topology. This is going to be the open sets on y, what I colored in blue here. The topology on y is going to be u intersected with y, where u is an open set in x. Here's a potential u. U intersected with y is that piece. That's open in y. That whole thing was open in x. It's going to get a little confusing because we're talking about two topologies simultaneously. This is in tau. That piece is in tau sub y. This is open in x. That is open in y. Notice that that blue part is not an open set in x necessarily.
Yeah, that's why. Why wouldn't it be? Is it if it's just a subset?
Because notice how the way I drew this open ball, it doesn't have this boundary, but I had y here including its boundaries. So that shape right there might not be open in x. The whole open ball is open in x, but the way it intersects y, it's no longer open in x. But it is now open in y. So how do we determine if a set is open in y? We say if it is the intersection of an open set with in x with y, then it's open in y. So sets that at first glance you might not want to call open because they're not open in x may still be open in y. And it's going to often be in including boundary points like that does. You might first look at that and say, no, that shouldn't be open in y because it has those boundary points. But it is in fact open in y. It's just not open in x. So this can get confusing because we're going to be talking about two topologies simultaneously. The topology on x and then the subspace topology on y. Everything colored in blue is a subspace topology on y, where the actual entire circles are in the topology on x. So read the definition one more time. Hopefully it makes sense. Let x tau be a topological space, and let y be some subset of x. We define tau sub y to be an open set in x intersected with y. U intersected with y, where u is in tau. It's open in x. Then y, together with this tau sub y that we just defined, is called the subspace topology of x. Is a subspace topology of x. There's infinitely many we could create if x were an infinite set. I didn't have to use this as my subset. I could have picked over here. I could have picked over here. I could have picked over here. So it doesn't matter what your subset is. For each subset, you have a potentially new subspace topology for it. We call V open in Y if and only if V is a member of tau sub Y. That's what we mean to say that that set is open in Y. We mean it's in Y's topology, not that it's in X's topology. So if you feel like you got the picture and the definition and ready to prove that this thing is in fact a topology, so far we've just been calling it a topology. We need to prove it is in fact a topology. That it still preserves these three properties that a topology has. Probably good to do a quick recap as to what is a topology. What are the three properties it has to have? Since it's been a little bit, let's just remind ourselves. Let's do a really concrete example. So pausing for a sec, just thinking about topology again. Let's say x is equal to set 1, 2, 3. And I want to create tau, so that tau is a topology on x. What does tau for sure have to have?
1, 2, 3, and the empty set.
It has to have the whole set x, right, in there. The set 1, 2, 3.
And the empty set.
And it has to have the empty set. If it just had those, we would call tau the trivial topology or the chaotic topology. Remember the chaotic topology, if you remember back to limit points, it's because anything converges to anything. So yes, this alone would be a valid topology. What if I put this set containing just 1 in there? Is it still a topology? We'll put this at the end and just keep adding things. Is that still topology? What were the other 2 things we had to check? So first property is the empty set and the entire set have to be in there for it to be a topology.
An arbitrary amount of intersections.
Almost. A finite amount of intersections and then an arbitrary amount of unions. Right. So take the intersection of any of those things. Do you get something in there? If I intersect those 2 together, I get the empty set. If I intersect those 2 together, I get the set containing 1. If I intersect those 2 together, I get the empty set.
That's good.
So far we're still good. What if I also added the set 1, 2 in here? You still good? Still topology.
Yeah, it looks like it.
What if I add the set just containing 3 in here? Is it still topology?
No,
No, why not?
because you can union 1, 2, the set containing 1, 2, and 3 and get a different, completely different.
If I union the set containing 1 and 2 and 3 together, I get the set containing 1, 2, 3, which is X, which is right there.
You're right.
So it works, right?
Yeah.
No.
What did I miss? Oh,
Union those 2 together, what do you get?
1 and 3.
1 and 3, so that's not topology.
That's correct.
Okay, so that was a quick timeout. Let's remind ourselves of the topology, go over a quick, really simple example before we get to this proof. So here we have a subspace topology. I need to prove that it is in fact a topology. In other words, this tau sub y thing, what do I need to show? I need to show that the empty set and that y are both in tau sub y. Because I'm saying tau sub y is a topology on y. I need to show that if v1, comma, v2, comma, dot, 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 comma, v sub n are all in tau sub y, then so is the intersection of all those things. And then I need to show that any arbitrary set, any arbitrary collection of things from there, if I union them up, it's still in there. So those are the 3 things I'm about to prove. So let's get started. So 1, let y tau sub y be a subspace. I'm not ever going to say subspace topology. I'm just going to say subspace, since topological spaces are the only spaces we're talking about. So let that be a subspace of x tau. Okay, 2. First thing I need to prove is that the empty set is in there and that the entire set y are in there. What are all the things that are in here? How do I know when something is in tau sub y? When it can be represented as u intersect y, where that u comes from tau. So then, if I want to show that the empty set is in tau sub y, I have to show that it is equal to u intersect y, where this u comes from tau. So I need to pick something from tau here that makes this true. So what's a set I can pick from tau that makes this true?
A set that is.
I need to choose something out of tau, an open set in tau, and I need it to be something such that when I intersect it with y, I get the empty set.
Would it be a space that is just in y?
If I take something that's just in y and intersect it with y, then I'm going to get something.
Yeah.
The empty set intersect y. Is the empty set in tau? Yeah. What's the empty set intersect y? The empty set. So I found something in tau such that when I intersect it with y, I get this set. So since this set can be expressed as an open set in x intersected with y, then this thing has to be in tau sub y. So that equal to that is in tau sub y. And we want to show that y is in there. What can I write y is equal to? I need y is equal to something intersected with y. And it needs to be an open set from tau.
Y intersect Y would be Y.
I'm not sure that y is open, so I can't just pick y. Y is just a subset. Maybe it's open in X, maybe it's closed in X.
Couldn't you take the entire set of U?
Just the entire set X. Is the entire set X open? Yeah. Y is a subset of X, so when I take X and I intersect it with Y, what am I left with?
Just Y.
Just Y. Now that looks ugly, so I want to say this differently. So, since the empty set is equal to the empty set intersected with Y, and Y is equal to X intersected with Y, comma, then the empty set is in tau sub Y, and the entire set Y is in tau sub Y. Remember, what is tau sub Y by definition? It's any open set in X intersected with Y. So here's X, here's my topology on X. What do I know for sure is in that topology on X?
Empty set?
Yeah, for sure this tau, for sure that tau, at the very least, has the entire set X and the empty set. And we don't really know anything else that's in there.
That's where, okay, I want to make, if we get crystal clear that a subspace is always inside of the,
Yes.
okay.
Y has to be a subset of X.
But I just don't understand entirely how Y can be equal to the intersection between X and Y.
I want you, so X is going to be students that go to the school. Y is going to be students taking geometry. I want you to tell me all the students that go to the school and take geometry. That's just the students that take geometry.
Wait, okay, so I got this flipped around. Y is the subspace, not X.
Y is a subset of X.
Okay, I had it flipped. I thought Y was
Okay. Let Y and tau sub Y be a subspace of X and tau. Okay,
Got it.
cool. So we just really showed for sure that the empty set is in tau sub Y and the entire set Y is in tau sub Y. So far it's looking good. Tau sub Y is looking like it might actually be a topology. Now what do we need to do next? I need to take a finite number of things out of tau sub Y, intersect them together, and somehow show that that's still in tau sub Y. In order for tau sub Y to be a topology. I'll keep writing until big on there, right now space. So let V1, comma, V2. As a general rule, I'll use V's for the open sets in Y, and U's for the open sets in X. Just natural convention. So let V1, comma, V2, dot, 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 up to V sub n. Not sure how many, but definitely a finite number, not infinite. All be members of tau sub Y. I tried to show that their intersection is also in tau sub Y. That's the goal. Now, if V is in tau sub Y, what do I know about a set in tau sub Y? How can I represent it? If it's in tau sub Y, remember, every set in tau sub Y is an open set in X intersected with Y. So I know that if V sub 1 is in tau sub Y, then that guarantees me that there must exist some U sub 1 in tau. Remember, tau is our topology on X, tau sub Y is our topology on Y. So if V is open in Y, then there must be some U, we don't need sub 1s here, then there must be some U open in X such that V is equal to U intersected with Y. I don't know what the open set is in there, but if V shows up in tau sub Y, there has to be some U in tau such that V is equal to U intersect Y. That's what it meant for V to be in tau sub Y. Tau sub Y are the collection of things that can be written this way. So then V sub 1 can be written as U sub 1 intersected Y. V sub 2 can be written as U sub 2 intersected Y. So what I'm getting at is let those in there, then there must exist u sub 1, comma, u sub 2, comma, dot, 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 comma, u sub n. Shoot, I hate putting stuff like this on the next line. In tau, sorry. Such that v sub 1 is equal to u sub 1 intersected with y. V sub 2 is equal to u sub 2 intersected with y, comma, dot, 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 comma, v sub n is equal to u sub n intersected with y. Each open set in y can be written as an open set in x intersected with y. So now we're going to take their intersection. I don't know why I went down so far. So then the intersection from I equals 1 to n, the intersection from I equals 1 to n of v sub I is equal to the intersection from I equals 1, keep drawing that to top, from I equals 1 to n of u sub I intersected with y. Do you remember this notation? Let's write this notation out a little bit more concretely just as a side note. If I'm taking the intersection from I equals 1 to 3 of a sub I, that's shorthand for writing a sub 1 intersected with a sub 2 intersected with a sub 3. So we're doing from I equals 1 to n of v sub I intersecting them all. So v sub 1 intersected v sub 2 intersected v sub 3 intersected v sub 4 dot 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 all the way up to n. N could be any positive number. Could be 10,000, could be 2. Any positive nat or integer, I mean. So then the intersection of those sets is equal to those. Now I'm doing a set intersected with y. Intersected with a set intersected with y. Every set I'm intersecting with y, essentially I'm saying the point has to be in here and it has to be in y. And the point has to be in the next one and it has to be in y. And the point has to be in the next one and it has to be in y. I keep saying over and over again it has to be in and it has to be in y. I only need to say that once. Or in other words, I can factor out this intersection with y. So see if you can follow it here. So that gives me the intersection from I equals 1 to n of all my u sub i's. So we intersect all those, and then when it's all said and done, we can just intersect with y. We don't need to keep intersecting with y as we go. We intersect with y when it's all said and done.
Oh yeah, that makes sense.
Okay. The logic for that is just anding the same thing over and over again. Remember, intersection is defined in terms of and anding the same thing to an expression doesn't change it. But anyways, now this, notice that this then must be in tau sub y. How did I just make that leap? Remember, these u's are now open in x. And I know that any finite intersection of open sets is open. So this is an open set in x. So I have an open set in x intersected with y. That's what it means to be in tau sub y. You're an open set in x intersected with y. This is an open set in x, it's intersected with y, so it's in tau sub y. So the intersection of these v's is in tau sub y. Make sense? And then it is literally almost identical logic for the union. So now let v sub alpha be any collection of sets in tau sub y. So take any arbitrary collection of open sets from y now. Maybe infinitely many, maybe just one. Again, that gives me that there must exist collections of sets u sub alpha in tau such that all my v sub alphas can be written as u sub alphas intersected with y. It's the exact same thinking we had up here. My v's can be written as u's intersected with y. My v's can be written as u's intersected with y. So now we just got union up the v's. So then when we take the union now, union up all those v sub alphas, that is going to be the same thing as unioning up all of those u sub alphas intersected with y. Now here we have to be a little bit more careful. What's the logic of what we're doing here? Remember that this is and, but union is or. So we're saying, writing this out a little bit, it's like we're doing, I'm going to index it, even though you can't really index it because it's an arbitrary collection, but we're doing something like u1 intersected with y, union together with u2 intersected with y, union together with u3 intersected with y, union together with ... That's what this is, right? Now, what we're basically doing is we're factoring an and out of a bunch of ors. So this is something that we proved in logic. We proved in logic that alpha or beta and gamma is equal to alpha and beta or alpha and gamma. That's how you distribute an or into an and, or in other words, how you factor an and out of an or. So we have it like this. We're factoring out basically the alpha. So we're doing alpha union together with a bunch of intersections. Am I thinking about that right? Let me rewrite this down the way that we have it. So we have it and here. So we're doing alpha and beta, or, we'll keep this one gamma. Gamma will be for y. Alpha and gamma, or beta and gamma. So if I have it like that, I can factor out the and we're left with alpha or beta and gamma. Okay, yes, I had it right there. Okay, so in other words, I can take all these and I can rewrite this as U1 union U2 union U3 ... and we're factoring out the and y like that. And so that's just using how you distribute an and over an or when we get down to the logic of it.
That's cool.
So now we can basically pull that and y out and put the union in. So this is equal to, I don't know if I have no space there. This is equal to, we union up all our u sub alphas first, maybe put parentheses there, and then we intersect it with y. Okay, so now, and then this is in tau sub y. How do I know that this is in tau sub y? What does it mean to be in tau sub y? It means you're an open set in X intersected with y. So we just have to ask ourselves, is this an open set in X? Well, what is this? Well, it's an arbitrary union of open sets in X. Is an arbitrary union of open sets in X an open set in X? Yes, that's one of the definitions of a topology. 3 definitions of a topology. You have the empty set, not definitions, 3 pieces to definition. You have the empty set and the entire set in there, any finite intersection is in there, and any arbitrary union is in there. So that's an arbitrary union of open sets in X. So it has to be open in X. So that's an open set in X intersected with Y gives us an open set in Y. So 7, therefore, tau sub y is a topology. Okay, so we just barely proved that these subspace topologies are in fact topologies. Well, that's good. I want them to be what their name implies there. Okay, let's do a couple definitions, then do some examples, get comfortable with these things before we move on to our next proof. So, remember with Rn, like R2 or just R, the real number line, we have a notion of the standard topology on R, right? So now if Y is a subset of Rn, we call the standard subspace topology on Y, the subspace topology inherits from the standard topology on Rn. So it's exactly what you would have guessed for this. So let Y be a subset of Rn, then the standard topology on Y is the subspace topology Y inherits from the standard topology on Rn. Pretty straightforward, right? Almost what you would have guessed if I would have asked you what's the standard topology on this subspace. Okay, next definition. Hopefully this sounds like I say the exact same thing twice in a row. If it does, I think you got it. Let Y be a subspace of X. We call some subset of Y, C. We call C closed in Y if and only if C is closed in the subspace topology on Y. How do I know that C is closed in Y? It's closed in the topology on Y. It's the complement of some open set on Y. Remember what closed sets are? We remember what closed sets are? What does it mean for a set to be closed?
It means that its complement is open.
It means its complement is open. What's complement?
It's the everything that's not included.
It's everything not in the set. It's like negating the set. Good. Okay. So with those two simple definitions, let's now go through some more concrete examples to get a feel for this thing. So we're going to look at Y being the closed interval from 0 to 1, and we're going to view it as a subspace of the standard topology on just R. So just R, we're talking about the real number line. There's R. The subset we're looking at is 0, 1. I just redrew it down here rather than drawing it on top. So here's our Y. Here's R. We're going to give it a subspace topology from the standard topology on R. Let's remind ourselves, what's the standard topology on R? How do I build open sets in R? Nothing? Open intervals. One-dimensional open balls. Right? So any union of open intervals is open in the standard topology on R. So I drew out some open sets in R. Call it U1, U2, U3, U4. These are all open in R. Let's draw them out really quick. This is the open interval from -1/2 to 1/4. Remember, if we do open parentheses like this, it means don't include the point. So that starts at -1/2, so it's this point, and it goes over to 1/4 is going to be like right there. There's U1. And maybe we'll color these ones in a little bit thicker so you can see it. So there's U1. Let's color in U2. U2 goes from 1/4 to 3/4. Probably should pick some better numbers. So that's here, to like right here. Filled in. Back to U2. U3 goes from 3/4 to 2. So there's U3, and then U4 goes from 3 to 4. Nope, those are all open sets in the standard topology on R. Now we're given Y, the subspace topology. So Y is inheriting its topology from X. Here's our Y, it's just 6. So what are the open sets on Y? Easy. We take the open sets on X and we just intersect them with Y. So if I take U1 and I intersect with Y, what do I get? If I take that interval and I intersect with that, I only get that little portion. So I get from 0 over here to 1/4. And it gives me this portion right here. So my V1 here would be including 0, not including 1/4. This is an open set in Y because this is an open set in X. Notice that V1 is not open in X. because it includes a boundary point. And notice that U1 is not open in Y. It has points that aren't even in Y. So this is open in Y, it is not open in X. This is open in X, it is not open in Y. Let's look at the next one. U2. So if I take 1/4 to 3/4 and I intersect it with that, what do I get?
The entire set U2.
You get U2 again. You just get 1/4 to 3/4 again. So that would be from here to here. Notice that in this case, an open set in X happened to also be open in Y. Now we intersect this with this, intersect this set with this set, what do we get?
3/4 to 1.
3/4 to 1, not including 3/4. So this is from 3/4 to 1, not including 3/4.
That's closed, right?
Closed. Well, closed meaning we include the one, but it's not a closed set, if that's what you mean.
They'd have to be closed on both sides, right?
For it to be closed in the standard topology on R.
Yeah. So what do you call it? It's not closed and it's not open.
A subset. Lots of subsets are neither open nor closed. So there's subsets that are both, there's subsets that are neither, there's subsets that are one, there's subsets that are the other. All these ones happen, all these ones are open in R.
Yeah.
That is not open in R, that's not closed in R. This is open in R, that's not open in R, that's not closed in R. Now let's look at this last one. If I take 3/4 and I intersect it with 0, 1, what do I get?
The empty set.
The empty set, which you'll notice is still open. So when I took an open set in X and I intersect it with Y, I still got an open set in Y. Just happened to be the empty set. So if I take an open set in X and I intersect it with Y, I get an open set in Y. Every time. That's how we define the open sets in Y. Sinking in?
Mm-hmm.
Picture yourself, the intuition sink in. All right, here's the test. We're going to look at Z as a subspace of the standard topology on R. So we're looking at the integers. Question, what is the topology that Z inherits?
You're only looking at the integers?
Yeah, we're only looking at the integers. So my set Y now, the set Y is going to be the integers.
Oh, I see.
It's dot 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 -3, -2, -1, 0, 1, 2, 3, 4. What's the topology on it?
It would just be like a bracket.
Well, let's think about something. So, we'll erase that. Let's just think about these. These are open sets in R, right? If I intersect this with R, with the integers, what do I get? So now let's think about V1, V2, V3, V4. But now our Y is the integers. So -1/2 to 1/4. I take that, and I intersect it with the integers, what do I get?
0.
The set containing 0. That's all I get. That's the only integer I get. Right?
Yeah.
I do 1/4 to 3/4. I intersect with the integers, what do I get?
Empty set.
Empty set. 3/4 to 2. I intersect with the integers, what do I get?
1. Just 1.
Just 1. We don't get 2, because it doesn't include 2, right?
Yeah.
Over here, 3 through 4. I intersect with the integers, what do I get?
Empty set.
Empty set again. Doesn't contain any integers. Okay, so it gives you a little bit of feel for it. So, what now is the topology, tau sub z, that I can get? Can I get the empty set? Yeah, we already did that just with one of our random examples. Okay, we got the empty set. Can I get the entire set of z, all the integers? Is the entire set R open?
I would assume so.
Yes.
Yeah.
The entire set always has to be open. So if I take all of R and I intersect it with Z, what do I get?
Just an empty
Just the integers. The integers are a subset of R.
Right. So, okay, yeah, the whole.
So I could get the empty set, I could get Z. We saw here I could get the set containing 0. I also got the set containing 1. Could I have gotten the set containing 0, 1? Is there some open interval I could find that gives me 0, 1?
That's correct.
What about just 2?
Yes.
What about 5, 99, and 1,276? Can I find an open set that gives me that?
Only the. No, I don't think so.
Okay, so I see where you're stuck. So let's reset. Could I find an open set that gives me both 3 and 5, but not 4? The answer is yes. I do this open interval union together with that open interval. Remember, any set of open intervals is still, any union of open intervals is still open.
Then yes, you can.
Yeah, so I can get 3 and 5. Is there any collection of integers I can't get? So I can get any collection of integers.
Yes.
So I can get every possible subset of the integers.
Yep.
So that gives us what topology? The discrete topology. The biggest possible topology. That gives us the biggest topology we could possibly get on the integers. And so now, think about that. We were able to define the discrete topology on the integers using the standard topology on R. Right? Viewing it as a subspace. But so it gives us a discrete one, or the power set would have been the best way to say it. The set of all possible subsets of Z. That's what we did. Okay. Cool. Those were some good examples. All right. Now, sometimes it's a little bit tedious talking about the entire topology in one go. We'd rather talk about a basis. Remember what a basis is? A basis for a topology is like the sets we can use to build a topology. Our basis for the standard topology on the real numbers is open intervals. The analogy I used when I first introduced basis elements was, think about like Legos. Our topology is all the possible Lego structures you can build. Our basis elements are each of the individual blocks. So maybe there's 2,500 different types of Lego pieces. Those would be our basis elements. And then our open sets would be any possible Lego structure you can construct, because it would be unions of the different types of Lego pieces that there are. So that's what a basis does. It gives us fundamental units to use to build our open sets. So we don't have to think about our open sets all in one go. We can just think about their basis elements that we use to build them. In the standard topology, that's just open intervals. So we want to come up with a way of talking about a basis on our subspace topology. And we want to somehow inherit a basis from the topology that it comes from. So that's exactly what we're going to prove here. So let y and tau sub y be a subspace of x and tau. Let beta be a basis for tau. So beta is a basis for the topology on x. And here's how I'm going to define beta sub y. Turns out beta sub y is going to give me a basis for my topology on y. I'm going to use a basis for my topology on x to define a basis for my topology on y. So let beta sub y equal b intersect y, where b is a basis element for x. So take all the basis elements for x, intersect them with y. That gives us a basis for y, it turns out. That's what I'm going to prove. So going back up to this example, my basis for the standard topology on R is open intervals. So what would be the basis for my y? Take all those open intervals and intersect them with y. Whatever I get, that's my basis for my topology on y. Okay. So we need to prove that that is in fact a basis. Now, remember, a basis has two properties. Probably been a while, so we don't remember what the properties are. How do I know if beta is a basis for a topology on x? So I have x and I have tau. How do I know that beta is a basis for that topology? For that topological space? It has two properties it has to satisfy. Property number one was, for any little x in big X, comma, there has to exist b sub x in beta such that x is in b sub x. In other words, every point in our set has to show up in at least one basis element. If I have a basis for the real numbers, one of my real numbers is pi. Pi better show up in one of those basis elements. If pi doesn't show up in any of my basis elements, it's not a basis. So this is saying for any, for all, for each, for any, is how we typically read that. For any x, for any little x and big X, there must exist some basis element in our basis such that x is in that basis element. If we're talking about the standard topology on R, let me rewrite this just for a standard topology on R. What would that be? That would be for any x in R, there must exist some open interval, b sub x now is an open interval in beta, such that x is in b sub x. Doesn't really change anything, just read it differently. If we think about this in terms of the standard topology on R, what does it mean for the set of open intervals to be a basis for standard topology on R? It means for any real number you choose, there must exist some open interval such that x is in that open interval. That's one basic property that a basis has to have. Every point has to show up in at least one basis element. Maybe more than one, but at least one. Number two, better seen pictorially. If I have two basis elements that intersect, now here's B1, here's B2. If I have two basis elements that intersect, then for any point in their intersection, little x, there has to be a third basis element, B sub 3, that contains x and is a subset of B sub 1 intersected B sub 2. So anytime two basis elements intersect, pick a point in their intersection, I have to be able to find a third basis element that contains that point, where that third basis element is a subset of the intersection. So those are the two things you have to prove if you want to prove that something is a basis. So with that, let's kick off. So let y tau sub y be a subspace of x and tau. And let beta be a basis for tau. So beta is a basis for our topology on x. And now, let beta sub y be all the basis elements in x intersected with y. So it's b intersected with y, where b came from beta, our basis on x. Then beta sub y is a basis for the topology on y. How do we prove that? I need to prove these two things. I need to show off first, every point shows up in there. And number two, anytime two basis elements intersect, then there's a third set containing their intersection. This is one way to do it, and we'll do it directly once. We're not going to do it with this one, but that was still worth having as a side conversation, because I will do that at one point tonight. Another way that we can prove that some set is a basis is give me any open set you want. I think in my case, I'm going to call my open set V. Pick any open set you want. So here's, that's stupid y. Here's y. Remember y, why did I write V? Remember y is some subset of x. So here's x, here's y. The other way that we can show that some collection of sets is a basis is if for any open set in the topology we're talking about, so here's an open set in y, which we're going to call V. If for any point in there, any point in V, I can find an open set containing that point, I can find a basis element containing that point where that basis element is a subset of V, then my collection is in fact a basis. So if I can find, so I've got some beta some y over here. So I've got beta y, which is a collection of sets. If for any point in V, I know V is open in y. If for any point you pick in V, I can look in here and I can find something. So I grab that out of here. I can find something that contains that point, and that something is a subset of V. Then this is going to be a basis for my topology on y. Because if I could do that for every point, if you would pick that point, I can find this one. If you pick that point, I find this one. Then I can represent V as a union of all those basis elements. And so we're unioning up basis elements to get our open sets, which is what you do with basis elements. You union them together to get open sets. Okay. So that's what we need to show. So I need to start out with an arbitrary set that's open in y, and then pick an arbitrary point out of it. And I need to prove that there is something in here that contains that point and is a subset of V. Then V can be represented as a union of all those things. It will eventually give me all the points back in V. And since any open set can be represented as a union of things in there, that thing is indeed a basis. We prove this as a side theorem. It's something like theorem 1.13. Probably should have rewrote out somewhere exactly what it says, but that's what the theorem is. So we'll be using that theorem rather than proving it's a basis directly, but there'll be another proof we do later where we prove something's a basis directly. So with that, let's kick this off. So let V be any open set in Y, and let little y be any point in V. So I've got some random open set, and I picked some random point in there. We know nothing about the point except that's in there. We're calling that point Y. Maybe for the sake of getting a better feel for all this, I'm going to draw my V like this. We're going to draw it over on the boundary here. So here's my V, here's my Y inside it. And that's just going to help us follow my proof a little bit better. So let V be any open set in Y, and let little y be any point in V. Well, since V is open in Y, then I know that V has to be the intersection of some open set in X, call it U, together with Y. So V is just this blue portion. But that's what it means to be open in Y. It means you're an open set in X intersected with Y. So I know that there must exist U in tau, an open set in X, such that V is equal to that U intersected with Y. Now, since beta is a basis on X, then there must exist some basis element from our basis on X such that Y is in that basis element, and that basis element is a subset of U. How do we know that? Since U is open in X and beta is a basis for X, then U has to be a union of basis elements. That's how we get topologies from bases. Bases? Something like that. So I know that there has to be some basis element in X, and maybe it happens to be this one, which I'm calling B. There has to be some basis element in X such that Y is in that basis element, and that basis element is a subset of U. So there exists B and beta such that Y is in B is a subset of U. Now, let B sub Y be B intersected with Y. So now B sub Y, running out of colors here, we'll color in with the purple as well. So B sub Y is going to be this portion. So that is our B sub Y. Let B sub Y be B intersected with Y. And observe that Y is in B sub Y. And B sub Y has to be a subset of U intersected with Y. Why does it have to be a subset of U? Because it's a subset of B, and B was a subset of U. And why does it have to be a subset of Y? Because by definition, it's intersected with Y. So it has to be a subset of that and a subset of that, so it's a subset of both. Okay. So then what did we just really show? So then we showed, since B sub Y is a subset of U intersected with Y, remember U intersected with Y is the same thing as V. What is V? It's U intersected with Y. So we just really showed that Y is in B sub Y, and B sub Y is a subset of V. And also note that B sub Y is in beta sub Y. What was beta sub Y? Over here, it's a collection of all our basis elements intersected with Y. Pick a basis element intersected with Y, it's in B sub Y. B sub Y is a basis element intersected with Y, so it's in beta sub Y. Therefore, beta sub Y is a basis. I just barely showed that for any point you pick in there, I can find some element in beta sub Y, in this case it was B sub Y, such that y is in v sub y and v sub y is a subset of v. Pick another point, I can do the same thing. Pick another point of v, I can do the same thing. Union up all those v sub y's, and that will give you back v. So v can be generated from these elements of beta sub y. It can be a bunch of b sub y's. So therefore, beta sub y is a basis. Okay, now with that, let's do some more feel-good examples. Because that's a lot of theory to follow. So now we're going to start defining topologies, subspace topologies, on these shapes that at first glance, not so intuitive how to do it. So we're going to start by looking at S1. S1 is how we represent the circle. So S1 represents a circle, and we're going to view it as a subspace of R2 with the standard topology. How do we think about R2? We think about that as a plane. So that was always the nicest because that's what the whiteboard gives us. So we're going to view S1 as a subspace of R2 with the standard topology. So notice here's S1 drawn in R2, and in blue I've drawn some random open sets in R2. That would be an open set in R2, that would be an open set in R2. If we look at how those intersect our circle, then they give us those open intervals. So now that would be an open set on our circle, and that would be an open set on our circle. Similarly, we can think about the torus in R3. What's the torus? The torus is a donut, but just the shell, no filling inside. It's hollowed out. So it's a two-dimensional figure, but we need 3 dimensions of space to draw. It's two-dimensional the same way that the surface of the Earth is two-dimensional.
Okay, yeah, I see.
Okay. So this is a two-dimensional object, exists in 3D space. What are open sets in 3D space? They're any weird blobs you can create that don't have their skin on them. Take some blob of area, peel off the skin, the boundary. That's an open set in R3. Well, intersect that with the torus, and it's going to give you these weird open patches. And so we can easily talk about topology on the torus, and I can draw that little figure there, and I can ask you, is that an open set? And you can look at it and say, yeah.
What's the torus?
This?
Oh,
Yeah, it's that the shell of a donut. It's called a torus. And similarly, I can give you this weird blob thing. Now this is meant to be just a surface, nothing inside of it. And again, this weird surface has some holes, no clue what to call it. But what would open sets on that thing be? Take these 3-dimensional figures, peel off their skin, and intersect them with that thing. And however they intersect, that's what's open. And so we can start pictorially telling real quick, yep, that's open, yep, that's closed. If I would have drawn this patch, where we include this boundary, don't include those, include that, don't include those, and filled it in, you can instantly tell me, nope, that's not open. Because there's no 3-dimensional figure I can take where if I peel off its skin and intersect with that, I still get those boundary points. And so you can quickly start to get intuition for what topology should look like on these different things. Okay, so there's some more feel-good examples. Now let's prove something that you would almost guess is the case. Remember that if a set is open, if U is open in X, then U intersected Y is open in Y. Right? And vice versa. If this set V is U intersected Y, where U is open, or sorry, if V is open in Y, then it can be written as U intersected with Y. And if U is open in X, what's the other way to say that? I think I said it right the first time. I think you know what I'm saying, but I'm going to mix up my words if I try and say it again. Open sets in Y are the same thing as open sets in X intersected with Y. That's the best way to say it. Similarly, you would expect that to be the case with closed sets. Is it also the case with closed sets? Is it true that if a set is closed in Y, then it can be written as a closed set in X intersected with Y? And it turns out, yes, that's going to be the case. For open sets, that was true by definition. That's how we define our subspace topology. We're going to be able to use that to prove it's the case for closed sets. So that's what we're going to prove now, is it is the case for closed sets. So remember, intuitively, how do we think about closed sets? Include the boundary points. So now, if we've got, as a general rule, I'm going to use D for closed sets in Y and C for closed sets in X. So if C is some closed set in X, forget about all these B's now. Here's Y's boundary. If C is some closed set in X intersected with Y, and you get this blue set, that should still be, D should still be closed in Y. And we're going to prove that that is in fact the case. And vice versa. If D is closed in Y, then it could be written as Y intersected with C, where C is closed in X. So we got to prove it both ways here.
So in this context, is C the entire circle?
C is this whole circle. D is the blue portion. Maybe if we do D in blue, it will help keep that clear.
So if you're saying that if C is a closed set, then the subset or subspace of C in Y is also a closed set. Or no, wait.
If C is closed in X, then C's intersection with Y, which is what D is,
Yeah.
then C's intersection with Y is closed in Y.
Okay.
Okay, so now I'm going to say basically the same thing. So let Y with tau sub Y be a subspace of X with tau. So tau is our topology on X, tau sub Y is our topology on Y.
Really
Y
quick.
is a subset of X.
Really quick. It's Y and X also closed sets. Just
X is just our whole set. So the whole set X is open and closed. Y is some random subset of X. So we kind of drew it close here, but you know, maybe it doesn't have those points. Maybe it has a patchy hole over here, so it doesn't include those points. Y is just some random subset.
so we don't know if it's closed or open.
We know nothing about Y except for that it is a subset of X.
That's probably where I was getting confused because you were doing solid lines for both.
Okay.
Okay.
Good. All right. So let Y with tau sub Y be a subspace of X with tau. So tau is a topology on X, tau sub Y is a topology on Y, Y is a subset of X. Then D as a subset of Y is closed in Y if and only if there exists C as a subset of X such that C is closed in X and D is equal to C intersected with Y. So it's an if and only if. So if I take a closed set in X and I intersect it with Y, I better get a closed set in Y. Similarly, if I start with a closed set in Y, there better be a way to extend it into a closed set in X such that when I intersect that with Y, I get back to D. So both ways here. So I'm going to prove this direction first. So let D be some closed set in Y. So all I know about D is it's a closed set in Y. That's it. Now if D is closed in Y, then the complement of D, Y minus D, is, if D is closed, its complement is open. That's a definition of a closed set. What does it mean to be closed? Your complement is open. So if D is closed in Y, then Y minus D, which is the complement of D in Y, Y minus D is everything in Y that's not in D. So then the complement of D is open in Y.
So this is where I get confused. When we look at when you made the statement D is a closed set, wouldn't that mean that the boundaries with the edges with Y have to also be closed?
So you're saying, so imagine that this was dotted.
Yeah, wouldn't that make D a subset, not necessarily open or closed?
Then D, as a subset of X, is not closed. But it's still closed in Y.
How do we know that? How does that make any sense? I don't understand.
Because its complement is open in Y. So I can be missing these boundary points. I couldn't be missing these ones.
How does that work? Oh, all right.
So let's And this is the scribble spot. So we'll scribble here. Let's draw this thing's complement.
Okay.
So D's complement, if we were to draw it, D's complement looks something like, and we're missing those points, we'll forget about that patch. So here's D's complement. This is open in Y. How do I know it's open in Y? If I can make it the intersection of some open set with Y.
Hold on. How is that D's complement? What about the L-shaped edge on the corner there? The other one.
What?
The complement, the intersection of Y's edge is also the complement, isn't it, of D?
The complement of D and Y. So I'm taking all of Y and getting rid of the points that are in D. Here it is.
Oh, the complement of D, Mike.
So over here we have Y minus D.
Okay.
I took the set Y, I got rid of all the points D. Here it is.
Okay, that's correct.
Now, is this open in Y? Can I represent this as Y intersected with an open set in X? And sure I could. I could extend it like this. This could be, I'm going to draw in purple the open set in X. So all those boundary points, so purple is open in X, right? I'm not including any boundary points on purple. And imagine I fit it all in X. We kind of tight on space.
Yeah.
Intersect it with Y, we get the black. So since the black here is an open set intersected with Y, by definition this black is open in Y. And so D is closed in Y.
Okay, so this whole time you were saying D is closed in Y and not necessarily that D is closed.
D is not closed in X necessarily. In this picture it certainly isn't.
Because we have the little...
Because of that little dinky there.
Okay.
If I fill that in, D would be closed in both X and Y.
This is where okay, so I see how the context is very important.
Yes.
D closed in Y.
Yes, that's why I was trying to show you when you erased the ones before. But you could have open sets in one that weren't necessarily open in the other.
Yeah, okay.
Similarly, you can have closed sets in one that aren't closed in the other. Good. Okay. So, I'm starting out with D, and I know that it is closed in Y. So that's my given. D is closed in Y. Work with it. So I say, okay, I know D is closed in Y. Well, what does that mean? That means D's complement, the thing we have written over here, has to be open in Y. It has to be in Y, the topology on Y. That's what needs to be closed. Your complement is open. So D's complement is open. It's in the topology on Y.
D's complement in Y is open.
Yes. Perfect. Now, if it's open, what does it mean to be an open set in Y? It means there's an open set in X that you can intersect with Y to get your set. How did I know that the black over here was open in Y? Because I could take Y and intersect it with the purple set. So the purple set here is our U. I take U and I intersect it with Y and I get this set. I think I may end up calling that set, do I ever name it? No, I don't ever name it, so it's just Y minus D. So Y minus D has to be able to be written as U intersected with Y, because it's open. So, then there must exist some U in tau, like that purple U, such that Y minus D is equal to U intersected with Y. Y minus D is open in Y. An open set in Y has to be able to be written as an open set in X intersected with Y. Now, I'm going to call C the complement of U in X. If U is open in X, then C is closed in X. So C is represented as going to be U's complement. So U is going to be equal to C's complement, If C is U's complement, U is C's complement. If C is everything that's not in U, then U is everything that's not in C. Or in other words, U is X minus C, where C is a closed set. It's everything in X that's not in C. That's what U is. Perfect. So that's the substitution we're going to make. We're going to replace that U with X minus C, where C is closed. So then Y minus D is equal to U intersected with Y. Then Y minus D is equal to U intersected with Y. Now we just distribute the intersection with Y to both of those. So X minus C, everything that's in X and not in C, and in Y, is everything that's in X and Y minus everything that's in C and Y. So just distributing the and over the subtraction sign. Something we proved clear back when we were doing set theory. So distributing the intersection gives us this. So X intersected with Y minus C intersected with Y. Now what is X intersected with Y? I want everything that's in both X and Y. Look at the picture. What's everything that's in both X and Y?
Y.
Just Y. So X intersected with Y is just Y. So Y minus D is equal to Y minus C intersect Y. So if Y minus D is equal to Y minus this thing, then D has to be equal to this thing. So D has to be equal to C intersected with Y. That's what we were trying to show, where C is closed. I was trying to prove that if D is closed in Y, then there exists a set C that's closed in X, such that D is equal to C intersect Y. And that's what we got. D is equal to C intersect Y, where C is closed in X. So we proved one direction here. We proved that if D is closed in Y, then there exists some closed set in X such that D is equal to C intersect Y. Now we need to go the other direction. We need to start out with our C intersected with Y and prove that the result is still closed in Y. So take something that we know is closed in X, intersected with Y, we need to prove that the result is closed in Y. That's the other direction. So this time, let C be closed in X, and let D be C intersected with Y. We're trying to prove that D is closed in Y. I know C is closed in X, we're trying to prove D is closed in Y. How do I prove a set is closed?
If its complement is open.
If its complement is open. So that's exactly what I need to do. I need to look at D's complement in Y and prove that's open. So I need to show that Y minus D is open. So if D is equal to C intersect Y, then Y minus D is equal to Y minus C intersect Y. Subtracting the same things from Y. Since those are equal, subtracting them both from Y. Good. Now, Y is the exact same thing as X intersect Y. I didn't change it by calling it X intersect Y. It's still just Y. So we have X intersect Y minus C intersect Y. Now I'm going to factor the intersect Y out. Before we factored it in, this time we're factoring it out. And so I get X minus C intersect Y. Now, let's think about this carefully. What do I know about C?
It's closed.
It's closed in X. So then X minus C is X minus C is the complement of C. So if C is closed, then its complement is open. So this is open in X. So I just barely showed that Y minus D, I showed D's complement in Y is equal to an open set intersected with Y. If it's an open set intersected with Y, then it's an open set in Y. So I showed Y minus D is an open set in Y, so D has to be closed. If its complement turns out to be open, then it had to be closed. We showed Y minus D is equal to an open set intersected Y. That's exactly what it means to be open in Y. I think I spelled it out a little bit more here. Let U equal X minus C, and observe that U is open in X, because it's just a complement of a closed set. So then Y minus D is equal to U intersect Y. And so it's open in Y, because it's an open set intersecting with Y. Therefore, D is closed in Y, because its complement was open. Any questions on that? Alright, let's move to the next board then. So the next section is on product topologies. Not sure how far we'll get. Okay, got all that in there. So now we're doing a product topology where we're taking cross products on topologies and getting a new topology. Now remember we're talking about the set cross product. Let's remind ourselves just real simple example of what the set cross product is. If I'm going to take the set 1, 2, 3, and I'm going to do the set cross product with A, B, what do I get?
An empty set.
No. I get the set of all ordered pairs you can possibly make where the first element comes from this set and the second element comes from this set. In a sense, taking a cross product increases the dimension. And so this, we have 1 paired with A, we have 2 paired with A, we have 3 paired with A, we have 1 paired with B, we have 2 paired with B, and we have 3 paired with B. Now imagine I already had topology defined on this thing. So tau 1 might have been something like the empty set, the set containing 1, 2, 3, and the set containing just 1. So maybe that was my topology on this thing, and maybe tau 2. Maybe tau 2 was equal to, we had the set AB, and then we had the empty set. We'll just give it the trivial topology. Is there some natural way of using that topological space and that topological space to give this thing a topology now? And that's what we're going to be doing. We're going to be taking existing topologies, taking their cross product, and getting new topologies from it. And it turns out there is going to be a natural way to do that. So that's what we're going to be doing in a very simple example. Now let's establish some intuition for how we actually picture these cross product things. So intuition. We're going to be taking cross products between topologies. I'm going to have some topology defined on X and some topology defined on Y. This is no longer going to be the case where Y is a subset of X. We're done with subspace topology. So now we're just going to have X as subspace with the topology and Y as subspace with the topology. Just like over here I had 1, 2, 3 might be your X and ABC might be your Y. Completely unrelated. And I'm going to be taking their cross products. So in general, we're going to be taking a topology on X and a topology on Y and somehow crossing them together. And we'll often be looking at subsets of them. So if A is a subset of X and B is a subset of Y, how do we picture their cross product? We picture it like this as that area. We need to take every point in A, pick some point in A, and I need to make all the ordered pairs that we could possibly make pairing with every point in B. And so crossing it with B gives me that line. And then crossing this point with B gives me that line. Crossing this with B gives me that line.
That's cool.
And so this is pictorially how we think about it. Now, obviously the set A could be the number 1, 2, 3, and the set B could be A, B, C. And then this picture doesn't really make a lot of sense. So this is just to help our intuition. We kind of pretend that we're talking about the standard topology on the real numbers or whatever, just for intuition's sake. So it's often how we picture it. Don't read too much into the picture. It just helps our intuition. Don't rely on it too much for proof. Okay. And then we'll also be looking at stuff like this. So here's X, here's Y. We might be looking at taking a couple. We might be looking at taking a set in X crossed with a set in Y, and another set in X crossed with a set in Y, and seeing how those two sets relate to each other. Maybe looking at their union, maybe their intersection. So again, here's pictorially how we think about this. So here's A1 crossed with B1, we think about as that area. A2 crossed with B2, we think about that area. Really quick, what would X crossed with Y look like pictorially? That whole top rectangle filled in. Okay. Now, I want to just point out two things to you. One that's nice and one that often breaks our intuition. So first off, notice this. If I take A1 intersected A2, that portion right there, and I take B1 intersected B2, so I take their intersections, and then I take the cross product, I get that where the two squares overlap, right? Notice that that's the same thing as if I started with A1 crossed with B1, taking the entire blue square, A2 crossed with B2, taking the entire pink square, and then did their intersection, I get the same square. So I could intersect A1 with A2 and intersect B1 with B2, and then take their cross product, and that's the exact same as first crossing A1 with B1 and A2 with B2, and then taking their intersection. With unions, it is not the case. And so this is what often hurts our intuition here. Notice, what is A1 union A2? It's this whole thing. And B1 union B2 is this whole thing.
That kind of makes sense.
If I were to then cross those together, that would include these orange areas. Right? On the other hand, if I start with A1 cross B1, which gives me the blue, and then I look at A2 cross B2, which gives me the pink, and then I union them together, it gives me everything inside there except the orange. This time we missed the orange. And so taking a cross product of unions is very different from taking a union of cross products.
That is true.
And so accidentally using this thinking can often get you in trouble.
So it's generally best practice to just do the unioning or the unions and intersections.
Well, it just
first.
depends on what you're talking about. Maybe you are wanting to talk about the whole square. Maybe you're not.
Maybe okay.
Just be careful what you care about.
True.
So it's not really here's what you should always do. It's if you meant to get the orange, then you meant this. If you meant to leave out the orange, then you meant this.
I see.
Okay, so now let's define how we create a topology. How we create a topology on a cross product. So we start with two topologies. We want to somehow get a new topology if we take their cross product together. Definition. So let X have a topology tau sub X, and Y have a topology tau sub Y. Completely unrelated from each other. Nothing in common that we know of. Then the product topology on X cross Y is generated from the basis beta, where beta is equal to the cross product between U and V, where U is any open set in X and V is any open set in Y. Now notice that this just gives us a basis. This doesn't give us a whole topology. Now, when you first come across this, you might say, shouldn't this just be all the open sets in our cross product topology? Shouldn't it always be the case that every open set is just an open set in X crossed with an open set in Y? And that gives me an open set in X cross Y? That seems natural and we want to think that. But let's pretend for a second that our X is R1 and our Y is R2, is also R. So X is R, Y is R, and we're crossing them together so that we can use this picture here. Notice that you would expect this shape right here that I have colored in, the union of those two things, to be open in R2. You'd want that to be the case. But notice that this shape, the blue and the pink together, that is not a cross product of two open sets. If I try and take the two open sets, that one, and cross them together, I get the orange. But we don't want to have to always include the orange. And so that's why this doesn't give us a whole topology. It just gives us our basis elements. And so I can define this blue square as the cross product of two open sets, and this pink square as the cross product of two open sets, and then union those together to get the shape that I want. So this just gives us our basis for our cross product topology. It does not give us a whole topology. So these are our basis elements, and then any union of those things is also open. And so we're able to recover this shape here. Okay, so that's some intuition. Not all open sets in product topology are products of open sets. Not all open sets in a product topology are products of open sets. This set the blue union together with the pink is going to be open to our product topology. It is not a product of open sets. I can't take an open set, cross with an open set to get that. Because then I'd get the orange that we erased. So let me repeat that. Not all open sets in a product topology are products of open sets. They're unions of products of open sets. They're always unions of products of open sets, but they're not necessarily just open sets crossed together. Okay.
What does products mean in this context?
Cross product. This cross product thing that we just talked about, that I started out with here. That crossing of two sets together, taking all their order pairs.
I see. So whenever you use the term product, you mean the cross product of these two things?
Yes.
Okay.
This has nothing to do with multiplication of real numbers. Just a name of an operation. Called the cross product. Yeah. It's one of those things you just have to get used to. Same symbols show up all over the place for different things. Okay. Our first theorem. So now, let X have its topology, Y have its topology, and let beta be all the sets U intersected with V, where U comes from tau sub X and V comes from tau sub Y, then beta is a basis. Notice what I said up here in this definition. I said beta is a basis for the product topology. I just called it a basis. I have to prove that it is in fact a basis. You can't just call something a basis and have it so. So I'm going to prove that it is a basis. I'm not going to use the theorem that we did last time. I'm not going to use the theorem that I erased the picture we had there. I'm not going to use the theorem that we had last time. This time I'm going to prove it brute force. I'm going to go back to the definition of a basis. I'm going to prove that every element in X cross Y shows up in a basis element. And I'm going to show that anytime you have two basis elements that overlap, pick a point in their intersection, there's a third basis element that contains it. I'm going to prove that those two properties hold for this beta, and so this beta is in fact a basis on X cross Y. Okay, so first I need to show that every single point in X cross Y shows up in at least one basis element. What is my basis? My basis is any open set in X you can pick, cross with any open set in Y you can pick. Pick any open set in X, any open set in Y, cross the two together, that's a basis element. So the first thing I need to show is that every single point in X cross Y shows up in at least one basis element. Now, in this case, it's really easy. Because the entire set, X cross Y, is a basis element. X is open in X, and Y is open in Y. So this is an open set in X, crossed with an open set in Y, so it's in our basis. Our basis element is defined as all the U cross V, where U is any open set in X and V is any open set in Y. So since the entire set in our case happens to be a basis element, that's convenient. We already showed every point shows up in at least one basis element. They happen to all show up in the same basis element in this case. That was nice. We had a catch-all. Okay, that shows the first property. Now I need to show the second property. So the second property, I need to show, maybe I can try and do this a little bit pictorially to help us keep track of what we're talking about. So again, this is the way we always picture it, this two-dimensional way, even though it can be misleading. So we've got our y's over here, our x is over here. This has nothing to do, by the way, with plotting on the xy coordinate system. It's just pictorially representing set. Y is sets, x are sets here. They start here and then go off that way, and we don't really think about any negative or positive or anything like that. Okay, now, I need to show that anytime we have two basis elements that intersect, then the point in their intersection can be captured in a third basis element.
So it's technically not even an order to X and Y, the set Y and the set of X.
Right, there's no order, they are points. Here's what one teacher did to really help my intuition in thinking about R2. He says, when we think about R2, for example, it's just points. You imagine R2 as this nice structure with all this beautiful geometry. He says, you think about R2 as like on a piece of paper, right? He says, take that piece of paper, run it through a blender into really fine dust powder. And take it, shake it up in your hand, and then hand it to me. is still the sets of all those points. It's still R2. All this other structure we just imagine all the time, and we never picture R2 without it. But R2 is just a set of all those points. We don't know where they are. Where, that's a geometric term. We have nothing to do with where. Now, in our case, we put a topology on them, so we preserve the proximity of them. So now we can't run them through a blender, but you can take that piece of paper and you can stretch it however you want. You can take one piece of it and stretch it all the way up to the moon. Doesn't change it. Still a topology. So we always impose all this structure on it, but strictly speaking, R2 is just a set. You can think of it, sets we often think about as powder in your hands. No clue how anything's sitting there related to each other. It's just a big set of stuff. So that's a good point. No order to the sets, nothing about the sets. But we represent this way. Okay, so what are we looking at? We're going to have two basis elements in our product topology. So I'm going to have, let me just skip ahead to see what I'm going to label. U1, U2, and X. Okay, so I'm going to have a U1 here, which I know is open in X. Maybe give more overlap so our picture can be drawn bigger. Hopefully we can, let me also do color coding so that we don't lose it. So I'm going to have U1 here, and that's going to be paired with V1. So that's going to be the set, and I'll do the other one in black. I'm going to have a U2 here, U2, and a V2. So U2 intersects with V2, that's going to give me this. This is going to be my second basis element. So blue here, this blue one, this is going to be my B sub 1 as one basis element. And my U2 intersected with V2, this is going to be my B2, this is going to be my second basis element. I'm going to pick some random point inside their intersection, some point right there, and show that there's a third basis element, B3, you can find, containing it, that's a subset of B1 intersect B2. And it turns out I'm just going to pick their intersection. That's going to be a natural one. Because their intersection, remember, that's still not going to include the boundaries, so that's still going to be a basis element. That's big picture how my proof's going to go here. So let B1 and B2 in beta, and let X comma Y be in B1 comma B2. So this is X comma Y is our point here. X, so it's X here, we chose that point, and Y here. Remember, it's an ordered pair because it's a cross product. So it's X comma Y, that point. So we pick some random point in their intersection, X comma Y. Has to be in the intersection. So then, there has to exist, I know since it's in B1, B1 is a basis element, so it's a cross product of two open sets. So there has to be U1 and B1, that makes B1, and there has to be U2 and B2, that makes B2. That's what it means for them to be basis elements. So then, there exists U1 and U2 as open sets on X, and there exists B1 and B2 as open sets on Y, such that B1 is equal to U1 intersect B1, and B2 is equal to U2 intersect B2. Exactly the picture I set it there. Okay. Let B3 equal U1 intersected with U2 crossed with V1 intersect V2. So U1 intersect U2 crossed with V1 intersect V2. That purple square. That's what I'm calling B3. And observe that X comma Y is in B3. I knew that X was in U1 intersect U2. So I know that we're good on the X coordinate. And I know that Y is in V1 intersect V2. So I know that Y, we're good on the Y coordinate. So X comma Y has to be in B3. And since B3 is just an intersection of sets that made these things up, then B3 has to be a subset of their intersection. B3 by definition is in B1, and B3 by definition is in B2. Because I just intersected those sets together. And notice finally that B3 is a basis element. How do I know B3 is a basis element? Because I define B3 to be an intersection of two open sets crossed with an intersection of two open sets. If I take two open sets and I intersect them, what do I get? An open set. So it's an open set crossed with an open set in X crossed with an open set in Y. That by definition is a basis element. That is where our basis elements are. Open sets in X crossed with open sets in Y. So B3 contains our point, and it's a subset of the two basis elements, and it is for sure a basis element itself. Therefore, beta is a basis.
I kind of wanted to bounce back here real quick. I was noticing this, you have the circle and then
Torus?
Above it. I was those are subspaces, correct?
Yeah, everything over there we're doing subspaces.
And I was observing that they were kind of outside of the circle. Can a subspace be like?
So what I was showing there is, notice that these blue sets are open in R2. And so where they intersect the circle, which I read you over here, those are open on the circle. These are open on the circle. Those are open in R2. Where they intersect the circle gives us an open set on the circle.
Okay,
so if we had a topology defined on that circle, what would be an open set in that topology? Those open intervals.
Yeah. Okay, so it just kind of made me wonder if I get what you're trying to demonstrate there, but it's not really what I'm asking. Can a subspace be in and out of a topology? Or is it the only part that's inside?
So in order to have a subspace topology,
That has to be completely inside.
you start with some initial space, which we call X. Your subspace has to be a subset of your initial space.
And it can't be partially out for any
It can't be partially out.
Okay.
If you go back to the first definition, Y is a subset of X.
Okay, just wanted to clarify.
Yeah, and so we often use subspace topologies to talk about topologies on objects that we can easily fit inside of some space. Typically, we're thinking about topologies on like surfaces that we can fit in three-dimensional space.
Yeah, makes sense.
Common example. Or, well, I don't know if I want to start talking about manifolds this early. But it's often how we picture like a, that could be a rabbit hole, I don't know. I don't dare do it because I'm not going to say it right and then it will lead to a rabbit hole trying to get it half decent.
We will be caught eventually.
Manifolds, if you guys hang in there, I will go to manifolds and I would be happy to start a manifolds class right when this class ends. Do manifolds, do smooth manifolds. I'm not sure how far we could go into differential geometry. That's a big boy field. You need some calculus for that first, so we somewhere have to stop. You also need linear algebra. So. You also need differential equations. You also need real analysis.
Well, I love learning what we're learning. I'm sure,
So
far I keep up.
yeah. There's what we call the baby maths sometimes. They just hold you up from doing everything. And so the baby maths are Calc 1, Calc 2, Calc 3, differential equations, and linear algebra. And those are kind of like the gateway maths to just, you kind of gotta get them out of the way if you want to do anything cool.
Yeah.
Anyways, I think we're here. Okay, so we defined our basis on our product topology in terms of open sets on X and Y. Could we have instead defined our basis on our product topology in terms of a basis on X and a basis on Y? Did we have to use all the open sets? Could we have just used their basis elements? And the answer is yes. And so that's what we're going to prove here. So let beta sub X and beta sub Y be basis on the, not sure how to say word class. Let beta sub X be a basis on X and tau sub X, and let beta sub Y be a basis on Y with tau sub Y. Then beta equal to B1 cross B2, where B1 is a basis element for X and B2 is a basis element for Y, is still a basis for our product topology. So in other words, here we kind of did it really simple. We said, throw in the cross products of any two open sets, collect them all together in a set, that's a basis element. Now we're saying, did we grab too many things? Do we really need to grab all this? Could we be a little bit more picky? And rather than grabbing every open set in X, could I have just grabbed its basis elements? And instead of grabbing every open set in Y, could I have instead just grabbed its basis elements and use those and generate our topology? And so the answer is yes, and we're going to prove that the answer is yes. But that's what we're out to do. Understand the problem, what we're trying to do, make it a little bit more efficient, make it so that we don't have to know all the open sets in topology. We can instead just know its basis elements and go from there. Okay, so let's do that. So I'm going to prove that beta is the basis for the product topology. Now I'm going to go back and use not the brute force definition, we're going to use our theorem again. How do I know if beta is a basis for some random topology tau? So I've got some random topology tau, know nothing about it, and I've got some collection of sets, beta. I want to know, is this a basis for tau? How do I check that? I pick any random set out of there, any open set U. So I've got some random open set U, and I pick any random point in there, little x. If for any random point I pick in U, I can find something in here, call it B. I can find some B in there, such that x is in B and B is a subset of U. Then beta is in fact a basis for this topology. Because I could generate U from a bunch of these B's. So that was B sub x which had x. Pick some other point in U, Y. If for that point I can go in there and find some basis element, this time call it B sub Y, such that B sub Y contains that and is still a subset of U. I can do that for every single point in U, get all these basis elements, union them all together, you get U. So U, any open set, can be generated from the elements in there. So beta is a basis for tau. So that was the theorem that we proved all the way back. Theorem like 1.13, I think. That's an older theorem, but we're going to use that to prove that this beta is in fact a basis. Okay. This one. Okay, so let W be any open set in X cross Y. And let X comma Y be any point in W. So remember, we're taking a cross product, and so our points now are ordered pairs. Okay, it's like if here's my X and here's my Y, X cross Y is this whole sheet. Okay, so let W be any open set in X cross Y, and let this be any point in W. I need to show that there exists something in beta that contains that point, where that something is also a subset of W. If I can do that, we're done. Okay. Now, since W is an open set, what do I know about W? I know W had to be generated from this basis. I'm going to prove it can also be generated from this basis. But since W is open in our product topology, I know it has to be able to be generated from this basis. So if I have a point in an open set on my product topology, then there has to be one of these basis elements that contains that point. So I know that there has to be some open set in X and some open set in Y, such that X comma Y are in those open sets, and those open sets are a subset of W. Since W is in our product topology, it had to have been generated from this basis. I'm proving it could also have been generated from this, but it has to have been generated from this. And so if a point is in W, it must have been in one of the basis elements that made up W. The basis elements that made up W look like U cross V, where U is open in X and V is open in Y. So there has to be some U that's open in X and some V that's open in Y, such that our point is in U cross V is a subset of W. Now, think about the topology separately. U is open in X, V is open in Y. Since U is open in X, then, since X is a point in U and U is open in X, then there must exist some basis element for our basis on just X, and there must exist some basis element for our basis on Y, such that X is in our basis element on X was a subset of our open set on X, and Y was in our basis element on Y was a subset of our open set on Y. gets tricky. We're talking about 3 topologies simultaneously. We're talking about the topology on X, which has its basis, beta sub X. We're talking about the topology on Y, which has its basis, beta sub Y. And then we're talking about the topology on X cross Y, which has its basis, which we're just calling beta. So 3 topologies all in one go. And we're always using U's for open sets in X and B's for open sets in Y. Okay. So I know that X is in B sub X. X is in a basis element on X, is a subset of the open set on X, and Y is in some basis element on Y, is a subset of the open set on Y. So now we define our B. What's our B going to be? Our new basis element is going to be our basis element on X crossed with our basis element on Y. And so then, X is for sure in B, not X. Observe that X comma Y. X comma Y is in B because X is for sure in B sub X and Y is for sure in B sub Y. So X comma Y is in B and B is a subset of W because its X portion is a subset of U is a subset of what made of W, and its Y portion, B sub Y, is a subset of B is a subset of the Y portion on W. So, since B is in this new beta we defined, remember this beta is an intersection of basis elements on X and Y. So since B is in beta, because we defined it to be a basis element on X crossed with a basis element on Y, that's what these are. So since B is in beta, then beta is a basis. I found some basis element containing the point where that basis element was a subset of our initial open set. We started out, let W be an open set containing a point. My job was to find a basis element. I did B, such that our point was in B, and B was a subset of W. That was the whole goal. And so I did it. Therefore, beta is a basis for X cross Y. So we don't have to use this as our basis. We can if we want. We could instead use a more restricted notion. Still works. How are we doing for time? Kind of at our end.
Be able to finish this right here.
These are 3 theorems. I have to prove them and then erase, prove, erase, prove, erase. And this next one takes a lot of drawing to understand. It's a lot, maybe that's a good one to come back to. A lot of drawing, so it will force you to remember both, because it ties in both subspace and product topologies. So maybe that will be a good one to come back to refresh us on all this stuff, throwing you into the deep end. Okay, any questions you want? Maybe skip ahead to the pictures since we have a few minutes, and then we can talk about the pictures again. Really try and cement in this intuition. So try and get you some of the usefulness now for these product topologies. We got a notion of subspace topologies and how they're kind of useful. Let's think about product topologies for a second. Well, a common one is we think about I as the closed interval 0 to 1. Well, now we can easily talk about the square. We just think about it as I cross I. Take all those points, cross with all those points, that gives us the unit square. It's often a useful example of a topology that we go back to, the unit square. You haven't seen us using these topologies as examples for future things. They'll come back and we'll use them a lot. So these will be some useful examples. Let's think about S1 cross I. So we start with the circle, and now I'm crossing it with I, which means for every point on the circle, I need to assign the entire interval I. So I go to this point on the circle, and I need to assign the entire interval I, which gives me that line right there. I go to this point on the circle, and I need to assign the entire interval I. I do that to this point, to this point, to this point, to this point, to this point. But I do that for every point on the circle, what am I left with? I'm left with all this, right? Kind of like a washer.
What is S1 exactly?
S1 is just a unit circle. Just a circle. Going back to over there.
It's like a unit circle above another unit circle?
No, it's just a circle. That's S1. Just a circle. This is a point in S1. This is not, this is not, this is not. It's just the actual circle. So it doesn't have the points inside.
Oh.
So it's a one-dimensional object.
Yeah.
So S1 is a one-dimensional object. Now I'm taking S1, I'm crossing it with I. So it means for every point in S1, here's a point in S1, I'm assigning it an entire interval. So I'm giving to that one point the entire interval, and to that point, and to the next one, and to the next one, all the way around. And so we're left with that washer shape. We call it the annulus.
It's not really how it works. They're more like a bunch of little tiny triangles at most. Not.
Triangles. So you're trying to think, the outside's kind of fatter than the inside, so you're forcing geometry on it.
Okay, I am, but you know, it's just not a washer then.
It is a washer because all these points, if you preserve the topology, this point has to be next to the point right next to it, has to be next to the point right next to it. You can't have any of those little gaps or you break the topology.
Yeah. Right.
So the cross product topology is going to force it to behave how you want it to behave. It's like a washer, but it's like a washer made out of rubber.
Okay.
A washer made out of rubber that you can somehow kind of inject mass into. So if you stretch it out, you can just grow the mass as needed to keep on going.
I see. So no matter, there really is no space between them, so it can go out. Two lines can go like this and theoretically be connected.
They're all going to be connected, going all the way around, to preserve the topology.
Yep.
Yes.
Okay.
So this is S1 crossed with I. Notice it's the same thing as I crossed with S1. So you take the interval. Now to every point on the interval, I assign a circle. So I assign a circle to that point. Now I go to the next point, and I assign it a circle. And to the next point, I assign it a circle. And if I keep doing that, it's going to regenerate the exact same shape. So I cross S1 is the same thing as S1 cross I. Now, if we do S1 crossed with the open interval, not including the endpoints, that gives us what we call the open annulus. And so, same thing, we just don't include the boundary. Moving on to the torus. The torus is S1 crossed with S1. It's a circle crossed with a circle. Remember, the torus is just the surface of the donut. So here's our torus, it's just the surface of the donut. Here's the way I think about reconstructing it. Think about just this inner circle right here. Forget the outer circle for a second. This inner circle is one of our S1s. And now to each one of those inner circles, I assign this blue circle. And I do that for every point on the inner circle. And as we go around, we regenerate the torus.
That's trippy.
Yeah, so gives us a way we can use simpler topologies to construct more complex topologies rather than starting out with the torus fresh.
Yeah.
So this is a common thing we do is we think about how you can somehow reduce a more complex topology to some of its more simpler forms. And this will make more sense next week after we talk about gluing things together with the quotient spaces. But last picture we want to talk about is S1 crossed with D. D represents the disk. So the difference between a circle and a disk is the disk includes all the points in the middle. So this time we start with a disk, a solid penny, and you wrap it around the circle. So rather than assigning just a hollowed out circle to each point, I now assign a disk to each point. So come back to, this is where I wish I could draw. So bird's eye view, we're looking at a circle.
Both those examples look like the same.
The difference here is, this is hollow. This is solid.
Oh, gotcha.
Okay, that's the only difference. So if you see that, then I think you see it.
I do see it now.
Okay. So introducing some of these pictures early on, it's good for you to get intuition about them because they're going to kind of keep coming up as common examples of topologies we want to talk about or figures we're interested in. Okay. Any other questions about any of that? Cool. Make sure your friends watch the lecture because next week isn't going to make a lick of sense if they